Welcome to Forging the Future, Decarbonizing the Steel Industry, a Hatch podcast series. I'm your host, Sakshi Sachdeva, and invite you to join us on a journey through the challenges and innovations in iron and steel production. Discover how Hatch's century of expertise is shaping a sustainable future for the steel industry. Stay tuned as experts from Hatch share their insights on technology, market dynamics, and the path to decarbonization. Welcome to Forging the Future, Decarbonizing the Steel Industry. Today, we are joined by two Hatch experts, Kyle Chomyn, Market Manager of Iron and Steel Technologies, and Gessa, a Process Specialist in the Iron and Steel Group. Welcome to the both of you, and welcome back to Gessa, second time on the show. We've been discussing the transformation of green steel and the technologies that are leading the pathway. Traditionally, the industry's looked at production of emissions as a solution to green steel. Keeping in mind the complexity and the scale of the industry, in your opinion, how would you define green steel? Are there any other dimensions you'd like to add to the definition?
Great question. So to me, green steel fundamentally means making our industry sustainable for our society and for our future generations. And sustainability is a very complex and multifaceted concept. To me, the foremost, of course, there's emission reduction and climate change driven, reducing our GHG emissions. But there's also other sort of sustainability dimensions beyond that. I think to me, the most important beyond just climate sustainability is, of course, environmental sustainability, which is slightly different, and of course, financial sustainability to the industry. Again, I think in the past few years, with a lot of focus on climate change-driven initiatives, emission reduction, transformations, and transitions in our industry, I think it's a new technology, a lot of investments in this field. But I think the other two aspects are somewhat sidelined in the conversation, which again are still very important. I think I'll cite one example. Again, today the most predominant concept of decarbonizing is to turn integrated BF-BOF processes into DRI-EAF steelmaking routes, which again today's most mature, established, and well understood low emission steelmaking pathways. Well, with it, even though there's a lot of decarbonization potential in that transition, it does come with a lot of environmental and financial sustainability challenges which still need to address. Again, I think the foremost of it to me is the waste generation aspect of it. Traditional BF-BOF integrated steel mills are very efficient of using materials, especially from the waste recovery and waste valorization perspective. That aspect is a bit lost and has yet to be optimized in the new DRI-EAF flow sheet. So there's a lot more waste generation and associated issues such as land use, pollution, natural resource consumption that come with this solution. So I think there's a lot of balancing to be done. And then, like I said, it's impossible to attain true sustainable steel making or green steel without focusing on all three pillars at the same time.
Mm-hmm. You touched upon waste generation. Could you elaborate on some of the different kinds of waste we're talking about?
For sure. So steelmaking as a process generates a lot of waste. Globally, about 300 million tons of solid waste a year. The majority of it is in the form of steelmaking slag, which are, again, molten solid oxides created in the steelmaking process, the electric arc furnace or basic oxygen furnace. Now, these wastes are, again, high volume, but they also contain quite a lot of iron oxide, usually 20, 30 or more percent by weight of iron. And these iron oxides are problematic because, one, they prevent these slag from being used effectively like blast furnace slag for cement making. But also, on the other hand, these iron units are the ones that you spend a lot of energy, time, and money digging out of the ground, beneficiating, reducing the iron, only to be thrown away in your steelmaking slag. So this really is a big problem for the steel industry in the way you store and stockpile and reuse and dispose of these hundreds of million tons of waste material, as well as associated iron unit loss that destroys a lot of economic value. So we see it as a very big wasteful and a huge potential loss in both the reusability of the chemical components of the slag, as well as the iron units you're disposing of. Now, there's a lot of technologies out there being explored how to better valorize, how to better reuse these steelmaking wastes. Things like stabilization, carbonation, aluminum-based recovery, to name a few. But they all have some of their limitations. For example, it's very difficult to scale them up to the million-ton scale a year that the steel industry requires. Some of them doesn't allow full recovery of iron units. I think that's where alternative solution is needed, and that's where the electric smelting furnace technology for slag valorization comes in.
Interestingly, we've talked about the electric smelting furnace on the show before, but never in the context of slag cleaning. So would you mind sharing more insights on the ESF and how it fits into this world of sustainable steel?
Yeah, the ESF is huge here because it's a complete solution. It's fully proven, it's highly reliable, and it's highly flexible. I mean, that's why it's been discussed in previous episodes, because it does have a lot of potential use cases, and it does have a really great opportunity to integrate to these existing flow sheets. So an electric smelting furnace, as the name implies, it's an electrically based furnace. It uses electrodes, kind of similar, you could say, to an electric arc furnace. However, where it differs is instead of being a relatively small, intense process, it's a much larger furnace, either rectangular configuration or circular, and it delivers power in a steady, quiescent bath type process, which allows you to have really high throughput, really high productivity. Ultimately, it gives you the opportunity to recover these useful materials, the iron from the slags and other materials, as well as converting the remainder into a really good product that can be used in the cement industry. So it's turning these two, multiple waste streams into really these two value-added components.
Well, it seems like the ESF is not only solving problems in the iron and steel industry, but also proposing solutions for the cement sector. From your perspective, how is that innovation being taken in the cement industry, and are there any opportunities for synergies between the two?
So that is a very important question, because I think this is sometimes understated. The cement industry today relies significantly on the blast furnace producers to get a blast furnace slag as a very important low-cost, low-emission, and high-performance raw material for cement making. As a rule of thumb, a blast furnace slag is about 15% cheaper than fresh Portland cement. It takes about 40% less energy and generates about 60% less emissions when you use that as a raw material to make concrete. So as the world slowly shifts away from blast furnace iron making to decarbonize the steel industry, that supply of low-cost, low-emission, low-energy intensity, high-quality raw material for the cement industry, the supply is dwindling. So I think in one sense, you can see it as the steel industry shift a focus on our own emission reduction. We're now sort of selfishly leaving the cement industry out to dry. So now they have to rely on Portland cement, which has, again, as I mentioned, cost, energy, and emission issue, but also a lot of natural resource and depletion risk as well. So I think with what ESF, slag valorization technology, really brings to the table is that not only can we make steel industry's emission lower, but becoming more sustainable, both climate-wise, environmental-wise, and financial-wise. It also help our brothers in the cement industry to help them decarbonize and move to a more energy efficient, more sustainable future. So I think this really is a win-win collaboration through this technology for two of the hardest to abate sectors to work together to achieve a sustainable society for us all.
And I think this is a really key aspect of all of this, right? I mean, Gessa talked about how the industry is losing this source of production from a blast furnace. And so we potentially need to replace it with something like an electric smelting furnace. But in a lot of ways, it's actually a net improvement over what's happening today. I mean, blast furnace slag sort of is what it is, and it just happens to work pretty well for cement. And so the industry has taken advantage of that. But in an ESF, you can actually fine tune, you can engineer that slag to optimize it for what's needed by the industry. So, I mean, of course, there'll be a learning curve to both industries using this slightly different looking product. But I think long term, there's an opportunity for further valorization of this stream of, cement replacement product for the cement industry.
To my knowledge, and correct me if I'm wrong, slag cleaning furnaces are not commonly used in the iron and steel industry. How did Hatch come up with ESF specifically for slag cleaning purposes? And more importantly, what does this introduction into the steel industry mean?
Yeah, that's a fair point, and it's true. I mean, for this industry, this will be new. For Hatch, electric smelting furnaces really go back to our foundation 70 years ago. Some of our earliest projects were with then QIT, now Rio Tinto, for their electric smelting furnaces in the ilmenite industry. And over the decades, our expertise has really grown in this area, and we branched out to many other applications of these high-power electric furnaces, such as slag cleaning in other industries, as well as platinum group metals and ferronickel applications. And ferronickel is where we've really seen the biggest advancements for the largest scale technologies that will be needed here. So we've developed this team internally that is really strong at delivering these projects, detailing all of the important aspects of the design to make sure it works robustly and works well. And that team also relies heavily on the broader Hatch team, such as our project delivery group, to make these things happen, as well as our friends in the Pyro process technology team to design flow sheets to make sure this is optimized and really achieves the best of what these technologies can offer.
I understand there's been years and years of work into the development of this technology. How mature is it today, and is it ready for commercial use?
As I mentioned, in other industries, this goes back many, many decades. But even when we look at iron making applications, this is really not at all new. This is something that's being done for over 100 years now. I mentioned the Rio Tinto furnaces. These are actually iron producing furnaces. There's also others such as Highfeld Steel, New Zealand Steel, Iron Dynamics. Again, these are all iron producing furnaces. So iron production is not new. Processing high slag volumes also is not new. These furnaces are used to putting through large quantities of slag, and really they've been optimized to do that. And over the decades, big improvements have happened. Hatch has been involved in a lot of them. One example is the introduction of high-intensity copper coolers to allow a higher density of power to be put into these furnaces. Another example is the development of the shielded arc process, also by Hatch. So Hatch has always really been at the forefront of these technologies, and that's why we're really well positioned to help bring this technology into the iron and steel industry to really make a difference.
How does it incorporate into the steelmaking flow sheet, more importantly?
So the electric smelting furnace is an extremely versatile, robust piece of equipment that can really fit into any steel plant to process slag and other waste. So the process and the equipment can be designed to take BOF or EAF slag of any sort. It could be charged hot or cold, crushed, granulated, molten or solid, or fresh slag made today or dug up from a legacy stockpile. So there really isn't much a limitation on that. And beyond just the primary feed, which is steelmaking slag from BOF or EAF, there's a host of other iron-bearing waste material generated on the plant that you can put into this process and co-feed it to extract economic value iron units and generate a blast furnace slag. And this, again, I cannot stress this enough, that the steel plant generates a host of different kind of waste materials. And the big, traditionally, all of these can be quite efficiently recycled in the sinter plant, but that's slowly going away as the steel industry transitions. So there's all these other revert materials. Some of them actually provides better economic value than the primary slag because of the iron content. I think, for the ESF process, the hot metal it produces with iron it recovers provides the majority of the economic value. So adding some of these reverts can really sweeten the overall economics of the process.
What sort of reverts are we talking about?
Yeah, there really doesn't have a limit on what kind of revert. So anything you generate on site, like I said, downstream wastes like the mill scales, a lot of other refining slags generated in the process, various fines and sludges and dust from the process. In the DR process, things like iron ore fines and DRI fines can all be recycled in it. And like I said, it really depends on customizing and optimizing the business case for the use of each type of these materials for the design case. For example, you have a higher iron unit or iron percent waste that can generate more hot metal, which is very favorable for the economic case. But on the other hand, if you have a specific stream of waste material that has a very high disposal cost, even though it doesn't have a lot of iron unit in it, it might make a lot of economic sense to recycle and eliminate that waste into your process. So I think overall, there's a lot of optimizing and customization that goes into designing the ESF process for individual plant and operation.
And I think this is really the key, because we've talked about how the technology itself is quite mature. So the key really is understanding the business case. So this is where we've been focusing over the last couple of years here, is doing case studies, talking to clients, understanding their various drivers. And what we found consistently is that this process is a really solid business case with order of 5 to 10 year payback period, which when you're looking at a green steel project, a sustainable project like this, that's really quite good. And I think it comes back to what Gessa said before, that the key here is to be environmentally sustainable. You also need to be financially sustainable. So this is really what we're driving at here, is to make sure that is the goal.
I'm glad you touched on the business case briefly. In your opinion, what kind of a business model do we need for this implementation to be a success?
So I think the waste valorization ESF has a lot of different business model it can thrive in. It really depends on what kind of operator is owning and operating one of these things. For example, because the ESF has a very high capacity, high productivity furnace, if you attach it to a DRI EAF operator's business, you can actually process more waste than a single large DRI EAF plant can generate. So then sort of a waste processing hub model could work, right? So you attach an ESF to a large DRI EAF steelmaking mill, and it can process all the waste it generates on site and also other mills from the region, turning into, again, the sellable slag for the BF industry, eliminating the waste and providing hot metal that can basically supercharge the EF operation, both from the productivity and quality perspective. Now you have the potential to eventually evolve into a zero waste, zero emission steel operation, which is, again, touching on all the sustainability pillars that we care about. If you're an integrated BOF operation that's traditionally recycling the sinter plant, so ESF mill then can slowly replace that in a way, again, recycling, effectively valorizing all the waste material generated in the plant while still providing high quality hot metal directly to the flow sheet. And this is especially important for integrated mill that do not operate a sinter plant for waste recovery, or that's hot metal short in from a productivity bottleneck perspective. So again, whether you are an integrated mill or EAF mill, the ESF has a role to play. And especially if you're an integrated mill looking at transitioning into EAF-based operation in the future, the ESF can transition the flow sheet along with it and play a supportive role in both flow sheets throughout and after that transition. So that allows your integrated mill to continue to sell slag to your cement off-takers even after the transition to perhaps a DRI EAF-based operation.
And I'll maybe jump in on that as well, that we talked in the past about DRI smelting operations using ESFs. I mean, fundamentally, the equipment looks very similar to what we're talking about there. So it also offers an opportunity for a long-term transition, as you might move to, say, a DRI ESF smelting route as well, or a mix of waste valorization with DRI throughput.
I mean, well, ESF seems like a promising solution for the path forward. Are there any challenges you're foreseeing?
Yeah, I mean, we've described this as being pretty easy looking. Obviously, the reality is that a lot of work will need to be done. This will be new for the industry. I think for the most part, the fundamental skills, both from an operations and maintenance perspective, but also from a business perspective, they're very similar to a normal steelmaking facility now. But of course, there are specifics around the ESF that operators are going to need to learn and understand. So to help with this, our plan is to offer comprehensive training programs, systems to allow them to really get up to speed quickly and ramp up quickly. And we've done this in the past. An example is for POSCO's affiliate company, SNNC. POSCO, of course, a steelmaking company, SNNC going into the ferronickel application with electric smelting furnaces. We designed and built their first electric smelting furnace. We developed a very detailed training plan and took them through that. And they were able to ramp up really rapidly, and they've become one of the world's best operators, I think large in part to that collaborative approach through the project lifecycle.
You mentioned that the furnace can process a wide range of waste materials. Gessa, you touched upon it earlier. From my understanding, there's minor elements that can transpire and cause issues downstream. Is the furnace capable of mitigating or managing these impurities?
So now you're talking about the quality of the products, right? So let's first talk about the slag. The slag is actually very precisely controlled and engineered inside the ESF from the composition, quality, chemistry perspective. Because on the other hand, the hot metal side, again, because it really depends on what the user is. depending on the user requirement, they may have different tolerances for impurities, qualities, and so on. And that's where I think a lot of the traditional technologies and practices done today for hot metal, things like hot metal pretreatment processes, can come in to really improve and add value to the product.
Yeah, and this is an important area where obviously Hatch has a lot of process expertise around the whole flow sheet, but we also have technologies we can offer in this space. So especially with us bringing on Kuttner a couple of years back, the Hatch Kuttner team actually has a proprietary design for a multi-refining, ladle refining process, which allows you to refine multiple elements in a single treatment step or station with multiple steps going on inside of that station. And ultimately what this does is it saves a lot of time in the process, which means money. It also saves capital cost compared to having multiple stations for each of the refining steps. And we've got a rich history of really delivering on these promises and these systems. We have over 70 installed references for these systems. So it's an area that where the case needs it, we can bring in those expertise.
Yeah. And just to be clear, again, the pre-treatment of the hot metal and adjustments chemical composition is really analyzed on a case-by-case basis based on the application. For example, if the hot metal is primarily feeding as a primary feed into a BOF-based steelmaking process, then you can do all the traditional desulfurization, desiliconization, dephosphorylation that's common to today's blast furnace hot metal technology. But if the goal is to co-feed the hot metal into an EAF, for a majority scrap-based steelmaking process, they'll probably have a higher tolerance of sulfur and phosphorus, so you do not require additional hot metal pre-treatment stage. And again, if your primary product is to be made into a pig iron for sale on the merchant market, then it has different drivers. So perhaps some of these additional hot metal pre-treatment technology can bring additional value for the price of the product. So really is a case-by-case basis, and we have a technology available to achieve all of these different outcomes should the business require it.
What does the downstream configuration look like following the slag cleaning furnace? Is it complex or similar to a blast furnace? I'm curious to know more specifically with regards to slag granulation.
Yeah, so it's very similar to a blast furnace. So I think anyone involved in the iron and steel industry knows, but on many blast furnaces, they have a water granulation step downstream. What this does is rapidly cools the slag, which makes it form a glassy phase, which is highly necessary for the use in downstream cement. And so this is something Hatch can do, and we have designed and delivered water granulation systems. But an area that I think is really exciting is actually air granulation. So whereas water granulation uses a water jet to rapidly cool the slag, air granulation does almost the same thing, except instead of a water jet, it's an air jet. And this brings some pretty important advantages. So first of all, of course, the elimination of water in this process. In many areas, water is quite expensive. However, even if water is not that expensive, you need to now deal with the dewatering, the water treatment before you're disposing of it. So that's a challenge that you just eliminate here. The other thing is because you're eliminating water, you don't form H2S like you do with the water granulated blast furnace slag, which is an issue that plagues a lot of plants with major health and safety issues or corrosion issues. And the third, because you're eliminating the water, you're not having the risk of steam explosions, which can happen, for example, in a loss of water event if you have a loss of power in water granulation system. So, I mean, the second two about the H2S and the steam explosions, these are issues that are largely mitigated through design and engineering controls in the systems for water granulation. But for air granulation, you just fundamentally eliminate these issues. So this is quite important. And then the other bonus here is heat recovery. But in terms of the development of this process, it's not new. So it was developed back in the 80s in Asia, and it's been used on a number of steelmaking applications. So, again, it's a fully proven technology. Hatch has been involved in this for quite some years now, and we actually now have 2 commercial references operating in the platinum group metal space. These are full-scale 2-ton per minute operations. And so, to give you context, this is the full scale necessary for, say, a 3 million ton per year electric arc furnace. So fully proven, mature technology. And a lot of opportunity for the integration here in the iron and steel space to further optimize this overall flow sheet compared to using water granulation.
Could you touch upon heat recovery a little more?
Sure, let me talk about it. So heat recovery really is a huge potential and opportunity for the slag valorization and air granulation process. I think traditional wet granulation process Kyle mentioned, you basically create a wet slag that needs dewatering before further use, but also a lot of lukewarm water that you really can't do anything with, can't recover the energy, and of course depletes water resources from an environmental sustainability perspective. So in the case of air-based granulation, what it does is creates a very hot off-gas stream on the order of 500 degrees or so, and an equally hot granulated slag stream. Now, energy can be very effectively recovered from both these processes for use around the plant, anything from raw material preheating, steam generation, and power generation. So it really adds a lot of value and doesn't require, and all these recovery do not require additional technology. All the energy recovery systems are very well proven and commercialized today. And I think a very interesting thing for me is that integrating air granulation with slag valorizer really opens up the door for great synergies between processes. For example, you can air granulate the incoming steelmaking slag, so you can create a hot slag that can be hot charged into an ESF, giving more energy efficiency to a slag valorization process. On the other hand, the product slag, the good slag, so to say, coming out of the ESF can also be air granulated. And now you have a high quality slag that can be sold to the cement maker. And the whole process doesn't require any water, and has plenty of places where you can recover energy to improve both the environmental and the financial performance of the system. So I think this is really where the most interesting synergies between all the great technologies out there come together to really improve, again, all three pillars of sustainability that I mentioned earlier.
I'm glad you tied it back to your original definition of sustainable steel.
Yeah.
Well, that's an interesting conversation. The ESF clearly represents a notable improvement to our existing blast furnace practices. We're nearing the end of our show today. I'd like to ask to the both of you any final message or takeaway points for our audience that you'd like to share.
Yeah, for me, again, I think it's tied to my initial point as well. Environmental and financial sustainability is equally important compared to climate sustainability. I think we really need all three pillars to be managed carefully, and hopefully we find great pieces of technology like the ESF that can tie all three drivers together to make green steel and sustainable steel making for our society true.
I think it's a really exciting time for the steelmaking industry. There's a lot of opportunity because of the changes that are happening. And I'm really proud about what Hatch is doing, and also what steelmakers doing, other technology providers. It's really great to see people coming together to try to tackle these big problems. And I really hope that 20 years from now, we look back and we say that our generation managed to make a really significant difference, not just to the steel industry, but really to the whole world by tackling these problems.
It's an incredible answer. Thank you both for your time and your effort today, and for this enriching conversation.
Thank you.
Thank you.
Thank you for joining us on Forging the Future, Decarbonizing the Steel Industry, where we navigate the complexities of iron and steel. We hope today's episode has provided you with valuable insights into the sustainable transformation of the industry. Remember, the path to decarbonization is a collaborative effort, and every step counts towards a greener future. I am your host, Thakshi Sachdeva, and along with the entire team at Hatch, we appreciate your engagement and curiosity.